Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we'd like to explain about still under flexibility method, chapter number 1. Now we're going to analyze frame with incline, load and member. Okay. Now we will analyze frame structure, which is they have incline, load and member. Still under chapter number 1, which is using flexibility method. Now let me consider the structure shown in figure here, which is they have joint A, B, C. On the member BC they have point load 50 kilonewton on the mid span of BC. Inclined member AB, they have inclined UDL 10 kilonewton per meter, given EI 50 kilonewton meter square. All the dimension given in question. At support A, they have a pin support. At support C, fixed support. So we're going to analyze this structure using flexibility method. And step number 1, we must calculate the DOI first. Okay? First we calculate DOI. 5 minus 3 equal to 2. It means this structure they have a 2 DOI. When they have a 2 DOI, it means you have 2 redundant forces. You have 2 redundant forces. When you calculate DOI equal to 2, it means you have 2 redundant forces. You have an option to decide your redundant force. Option number 1, you can choose AX, reaction AX and AY as your redundant, or option number 2, you can choose CX and MC, CX and MC as your redundant, or the third choice, you have AX and MC as your redundant. For option number 1, let me proceed with option number 1, where we choose AX and AY, or reaction at A in X and reaction at A in Y as our redundant forces. When you choose AX and AY as your redundant forces, it means you must remove the AX and AY. You must remove the AX and AY to form your primary structure and redundant structure. Because the next step, you must apply the principle of superposition. The next step, or step number 2, we will apply the principle of superposition, which is principle of superposition means actual structure equal to primary structure plus redundant structures. Redundant structures here, they have a 2 structure because we have a 2 DOI. Okay, we have 2 DOI, so your redundant structure you have 2. The term principle of superposition means actual structure equal to primary structure plus redundant number 1 plus redundant number 2. Now, please bear in mind, actual structure is an indeterminate structure. Primary and redundant structure is a determinate structure. Why primary structure and redundant structure determinate? Because you have reduced the redundant forces AX and AY. When you choose redundant forces AX and AY, it means you will reduce AX and AY from actual structure. You remove AX, you remove AY. That's why your primary structure now, they have no reaction here, because you remove AX and AY. Similar to redundant number 1, you remove AX, AY, and redundant number 2, you remove AX and AY. Then it means for primary structure, redundant structure, you have the same structure. The difference is between primary, redundant number 1, redundant number 2 in terms of loading system. For primary structure, you apply all the real load, all the actual load you apply on primary structure, which is you have a 50 kilonewton and UDL. For redundant number 1, since redundant number 1 associate with AX, so you apply 1 unit load FA in X direction. For redundant number 2, this structure associate with AY, that's why you apply 1 unit load force at A in Y direction. Okay. Next, we are going to determine the bending moment equation for primary structure, redundant number 1 and redundant number 2. Why we need to determine this bending moment equation? Because if we look at our general compatibility equation, when we talk about compatibility equation, this equation deal with displacement or deformation, delta 1, delta 2, delta 1, 0, delta 2, F11, F12, 21. It means this is about the displacement. How to calculate displacement? To calculate the displacement, you must consider the bending moment equation first. That's why the next step we will calculate the bending moment equation. Okay. Next, we start with step number 3. We determine the M0. M0 means we refer to structure for primary structure. Okay. Before we start our bending moment equation, we must decide how many cutting we should have for the every structure. Okay, we must decide how many cutting we should have. To determine how many cutting we should have, we must refer to actual structure. Okay, we refer to actual structure just to determine how many cutting we should have for primary structure and redundant structures. Okay, clearly by inspection, when you refer to actual structure, they have a one cutting for member AB, one cutting also, another one cutting for from B to the load 50 kilonewton, and the other cutting for 50 kilonewton to the C. It means you have 3 cutting. So that 3 cutting must appear on primary structure and redundant structure. Cutting number 1, cutting number 2, cutting number 3. Okay. The cutting limit and to consider left hand side structure or right hand side structure must similar for primary and redundant. I repeat again. Number of cutting, limit of the section, and to consider left hand side or right hand side structure for primary and redundant, they must have the same cutting and same limit and same origin. So next, we start with the cutting number 1 for primary structure. For cutting number 1, I stated here origin at A. When I stated here origin at A, it means I will consider left hand side structure. Means when you do the cutting, I consider left hand side structure. Similar to cutting number 2. When I do the cutting here, I consider left hand side. Similar to cutting number 3, I consider left hand side. It means for all three cutting here, I consider left hand side structure. So for cutting number 1, the limit is 0 to 3. It means I consider X in horizontal direction, not follow the inclined member. If I follow the inclined member, the limit is 0 to 5. You can do that. But for this solution, I choose X 0 to 3. Okay? You have an option to consider X follow the length of AB. But now, for this solution, I choose X from horizontal direction 0 to 3. That's why when you refer to this limit here, I stated here 0 to 3, and X you follow the horizontal. Okay. Next, when you do the cutting number 1, MX is a balancing moment. When you do the cutting, you the load on your system after you do the cutting, you have one load only, which is incline UDL 10 kilonewton per meter. Since you consider this is your X, to make it easy for our calculation, I determine the relationship for this triangle. When we have a 53.13 angle here, so you consider tangent, you have 1.33x here, and you consider cos 53, so you have a 1.7x here. Okay, this is as a guide when you calculate the bending moment equation. Okay, so we consider bending moment equation at cutting number 1. Okay, it means we calculate bending moment equation at cutting number 1 at this point. Okay, at this point. So all of the load you will calculate using the dimension from the load to the cutting number 1. Okay, so this is summation of moment at cutting number 1. Clockwise, we consider positive value. So that's why we start with the minus mx, because this mx anti-clockwise, minus mx, and then this incline UDL I will resolve in vertical direction and horizontal direction. Okay, that's why they have a two term here in your equation, because this is vertical component and the other is a horizontal component. 10 multiplied by 1.67x, it means 10 intensity of this UDL multiplied with the length, this length 1.67x, 1.67x. Okay, 1.67x. After 10 multiplied by 1.67x, it means it looks like you have one imaginary line point load here, one imaginary line point load here. So to resolve in vertical direction, that's why cos 53.12, when you multiply by cos 53.13 actually, so you have a vertical component. This vertical component is a force, and ask yourself where you want to calculate your moment. So you want to calculate moment at cutting 1, so you must have this dimension from the force after you resolve to cutting 1. So the force is x divided by 2. Okay, x divided by 2. That's why 0.5x. Okay, this is from the force in the vertical component. Next, in the x component. Okay, x component, 10 multiplied by 1.67x. Okay, 10 multiplied by 1.67x means UDL, you multiply by the length for the UDL, 1.67x. You have a one imaginary line for inclined force. Then to determine the component in x, that's why you multiply with sine 53.13 here. Then after you multiply with sine 53.13, you have a force in x direction here. Okay, the direction of force in x direction. Okay, in x direction. So you must multiply with this dimension. This dimension equal to 1.33x divided by 2, because load applied at the midspan here. Okay, that's why you multiply with the 1.33x divided by 2 equal to 0. Then you resolve this equation to your bending moment equation now. Mx equal to minus 5x squared minus 8.88x squared and equal to minus 13.88x squared. Okay, this is a moment equation for primary structure for cutting number 1. Then we go for cutting number 2. Okay, your cutting number 2 between B and force 50. This is your cutting number 2. Again, we consider left hand side structure, which is A as your origin. You do the cutting here. Similar what we did for cutting number 1. We calculate moment, summation of moment at cutting number 2, and clockwise moment as a positive value. That's why we start with minus mx, because this is balancing moment, anti-clockwise, minus mx. And again, we consider incline UDL for member AB. But now, you're cutting not at the UDL like cutting number 1. Now, you're cutting on the member AB. So, you must consider for the whole UDL on member AB. That's why, for this calculation, when you want to consider this UDL, 10 multiplied by 5. Okay, 10 multiplied by 5, because you consider for the whole length. This is 5. 10 multiplied by 5. After 10 multiplied by 5, you have an imaginary line here. It looks like a point load at the midspan. Point load. Okay, so this point load. Next, we determine the y component and x component as mentioned in cutting number 1. So 10 multiplied by 5, you consider cos 53.13. Cos means you consider vertical direction, vertical component, and multiply with distance. This is the distance. X minus 1.5 is a distance. Distance force to cutting number 2, because your force act at this line, and the distance is from the force to the cutting number 1, which is x minus at the back 1.5. Okay, because your force, because this is x, and your force here, so x minus distance at the back here 1.5. Okay, 1.5, because your length here is 3 meters. So when you consider load at midspan, it means 1.5 here. That's why x minus 1.5. That's why you have a x minus 1.5 here. And then you consider horizontal, or in x component, 10 multiplied by 5 sine 53.12, and you have a force this direction. Okay, this direction. This direction multiplied with the distance. Okay, please bear in mind that distance must perpendicular to the force. Okay, so the total length here is a 4. The total length is a 4. So half means 2. Half means 2. So you resolve this. So you got the mx equal to minus 30x minus 35. Then we go for third cutting. Again, we consider origin at A. It means we consider left hand side structure, and your limit now 6 to 9. Just now limit 3 to 6. Okay, 3 to 6 means this cutting number 2, this limit when you consider A as origin. So from 3 to 6. Cutting number 3 from 6 to 9. Okay, so your free body diagram look like this when you consider left hand side structure. Again, the principle is similar for cutting number 2 and cutting number 1. You summation of moment at cutting number 3, and you consider clockwise moment is a positive value, so this is minus mx minus, again this is I'm consider resolve force in y direction, 10 multiplied by 5 cos 53.12. This is we consider force. 10 multiplied by 5 cos 53.12. This is component force in y direction, multiplied by distance. Distance is a x minus 1.5, because your force here, distance from here to cutting means x minus 1.5. That's why you have it like this. Then you consider component x, which is 10 multiplied by 5 sine 53.12. Then this force act at the midspan of your incline here, this force, and distance from here to here, from the midspan of member AB to the cutting. So full length equal to 4 when the force act at the midspan, so that's why your distance here is 2 meters. Then you consider this 50 kilonewton load, point load, force multiplied by distance, force multiplied by distance, 50 kilonewton multiplied by this distance equal to x minus 6, x minus 6. That's why you have a 50 multiplied by x minus 6. 50 force, x minus 6 distance, because moment equal to force multiplied by distance. Force and distance must perpendicular. Then to solve this equation, so mx equal to minus 80x plus 265. Okay, settle our bending moment equation for primary structure for cutting number 1, cutting number 2, cutting number 3. Then we go for the second structure, which is redundant structure number 1, M1, cutting number 1, number 2, number 3. Please bear in mind origin and limit, you must follow the primary structure. Okay, we must follow the primary structure. For redundant number 1, your structure look like this. Your structure, and you have a 1 point load. 1 point load you apply at A in X. Okay, when you do the cutting number 1, number 2, number 3. Of course, cutting number 2 and number 3, they have a same moment equation. Okay, they have a same moment equation for cutting number 2 and number 3, because there's no change in load for this member. Okay, so when you look at the cutting number 1 for M1, your structure, when you consider left hand side, your structure look like this. Okay, so again, you calculate moment at cutting number 1, clockwise moment as a positive value, so minus mx minus 1 multiplied by vertical distance here. As we discussed for the previous, vertical distance, when you consider this is your x, the vertical distance is the 1.33x. That's why this minus mx minus 1 multiplied by vertical distance here, 1.33x. So you have a mx equal to minus 1.33x. For cutting number 2 and cutting number 3, number 2 and number 3, they have a same moment equation. Your structure look like this, where you have a 1 point load here. When they have a 1 point load here, and this is your cutting. Again, you calculate bending moment equation for cutting number 2 and or number 3. Clockwise moment as a positive value. That's why you have a minus mx minus 1 force 1 multiplied by distance. This distance equal to 4. Okay, this distance equal to 4 because you have a full distance here. 1 multiplied by distance 4. That's why you have 4 here. So mx equal to minus 4. Then settle for redundant structure number 1. Then we go for redundant structure number 2. Okay, redundant structure number 2, which is this is your redundant structure number 2. This is your redundant structure number 2, which is you have the same structure, but now your loading system, you apply 1 unit load at A in Y direction. Okay, at A in Y direction. So that's why your redundant structure number 2, when you do the first cutting, look like this. They have a 1 point load 1 kilonewton at A in Y direction. Again, we calculate moment at cutting number 1 clockwise as a positive value. That's why you have a minus mx, then plus moment from this 1 kilonewton multiplied by this distance, horizontal distance, 1 kilonewton multiplied by this distance equal to x. Okay, 1 multiplied by x positive value. That's why you have a x here. So mx equal to x for cutting number 1. For cutting number 2 and number 3, you do the cutting here and 1 point load here. So moment at cutting number 2, number 3, and you consider clockwise moment as a positive value. So minus mx plus x. How to get this x? 1, again 1 multiplied by this distance x. This distance x. Okay, that's why. So that you get the mx equal to x. Then after you have determined bending moment equation for primary structure, redundant structure number 1, redundant structure number 2, for cutting number 1, for cutting number 2 and number 3, then you tabulate all the bending moment equation in the table form. Okay, M0, M1, M2, cutting number 1, cutting number 2, cutting number 3. Then step number 4. Step number 4, we calculate the deformation, because I've mentioned just now, compatibility equation. This is equation about deformation. Delta 1, delta 2, delta 1, 0, delta 2, 0, F11, 1, 2, 2, 1, 2, 2. This is about deformation. This is deformation for the actual structure. This is deformation for the, this is deformation for actual structure. Delta 1, 0 and 2, 0, deformation for the primary structure. 1, 1, F12, 2, 1, 2, 2, this is a deformation for the redundant. Redundant number 1 and redundant number 2. So, that's why you must, step number 4, you must calculate the deformation. How to calculate the deformation? This is the way how to calculate the deformation. Please refer to equation in our note. If I'm not mistaken, they have equation in slide number, if I'm not mistaken, slide number 7, or something you have learned from the previous subject under determinate structure. Okay, so you press your calculator, then you can determine this value delta 10, 20, F11, 1, 2, 1 and 2, 2. Delta 10, what means? Delta 10 means to calculate integration of 1, 0. It means integration of M0 multiplied by M1. Delta 20 means integration of M2 multiplied by M0. F11 means integration of M1 multiplied by M1, and so on. Okay, then after you determine the deformation, then you substitute into our compatibility equation. We substitute into our compatibility equation. Just now I've mentioned here general compatibility equation. Okay, this is our general compatibility equation. You must determine all of this value, deformation. So after you have determined this deformation, you substitute into general compatibility equation. Then after you substitute, your equation look like this. Why delta 1, delta 2 equal to 0? Because delta 1 and delta 2, this is deformation for actual structure. Deformation for actual structure normally equal to 0 where they have no support movement. When they have no support movement, or they have no fabrication error for member, this value equal to 0. Okay, delta 10, delta 20, F11, F12, F21, F22. So you substitute all of this value, then you can press your calculator. Then you can determine delta X equal to 18.33 kilonewton, delta Y, AX or reaction at A in X equal to 18.33 kilonewton, reaction at A in Y equal to 54.4. Then after you have determined these redundant forces, then you can determine the remaining reaction. Okay, after you determine the AX, AY, then you can determine the remaining reaction CX, CY, MC here. So this structure look like determinate structure. Okay, so for determinate structure, by using three static equation, so you can determine MC, CY, and CX. Okay, until here it means done for us to determine or to analyze the structure, which is our objective is to determine the support reaction. And for our actual structure, we have a 5 support reaction, 2 at A and 3 at C. Okay, now we have determined at A, this is the value, at C, this is the value. So done. Now I go for the option number 2. Option number 2, when we choose CX and MC as the redundant force. Okay, CX and MC as our redundant forces. So when we choose CX and MC, okay, I repeat again, when we choose CX and MC as our redundant forces, it means you must remove the CX and MC from your actual structure to form your primary structure and redundant structure. That's why if you refer to your primary structure, at A remain as a pin support, but at C originally they have a fixed support after you remove CX and MC. That's why at C here they have a roller support, similar to redundant number 1 and redundant number 2. Okay, when you remove CX and MC, okay, redundant number 1 associate with CX, redundant number 2 associate with MC. So for redundant number 1, since you remove CX, now you must apply 1 unit load at C in X direction. That's why they have a 1 kilonewton here. For redundant number 2, the same structure for the redundant number 1 and primary structure, but now since you have removed MC, M means moment, so that's why for redundant number 2 associate with MC, you apply 1 unit moment, kilonewton meter, 1 unit moment at point C. Okay, at point C. Then you calculate all the reaction. Okay, then you calculate all the reaction, 4 over 9, 1 here, 4 over 9 here, 1 over 4, 1 over 9, I think 1 over 9, 1 over 9 here. This is the reaction for our redundant structure. Then as for option number 1, next we will calculate, we're going to calculate the moment for primary structure, moment for redundant number 1, and moment for redundant number 2. Okay, for primary structure, we do the cutting number 1. We decide to choose this is cutting number 1, this is cutting number 1, this is cutting number 2, and this is cutting number 3. And for this option number 2, I choose for cutting number 1 and number 2. For cutting number 1 and number 2, I choose C as our origin, and for cutting number 3, I choose A as our origin. So you must consider for primary structure redundant number 1 and redundant number 2. Okay, if you choose cutting number 1 and number 2 to consider right hand side structure, so you must do the same for redundant number 1 and redundant number 2. Okay, For primary structure, this is cutting number 1. Okay, when you do the cutting number 1, you consider a right hand side structure. Your structure look like this. This is your balancing moment clockwise, because you consider right hand side. When you consider left hand side, your balancing moment anti-clockwise. When you consider right hand side structure, your balancing moment clockwise. Okay, so next we calculate the moment equation at cutting number 1. Okay, we calculate bending moment equation at cutting number 1. So you consider mx clockwise positive, mx minus 47 multiplied by x. So you have this moment equation. Then for cutting number 2, you do the cutting number 2 here, and of course you must consider 50 kilonewton here, and this is your balancing moment. Limit 3 to 6, just now 0 to 3, mx plus 50 multiplied by this distance. This distance equal to x minus 3. Okay, 50 multiplied by this distance. Okay, moment from this 50 equal to 50 multiplied by this distance, x minus 3. So you have a 50 multiplied by x minus 3 here. Then you consider this 47.22 reaction, minus 47.22 multiplied by distance x. Okay, you have this equation. Then cutting number 3. Cutting number 3, you consider left hand side structure, origin at A, and of course for this cutting number 3, for option number 2, I'm consider x, this x, I follow the length of the member. Okay, you have an option, even though you want you cannot consider this x horizontal here, like what we did for option number 1. But now I consider x follow this member to show to you all that this x not rigid to consider in horizontal direction. We can follow the length of the member also. Okay, so when I consider x follow the member, so that's why limit here is 0 to 5. Okay, 0 to 5. So cutting number 3, this is your balancing moment. Now I'm consider left hand side structure, that's why balancing moment anti-clockwise. You have a reaction here for T 32.78, and you have a UDL here. Okay, 40 and 32.78, this is a reaction here. Okay, you calculate a reaction here due to this system. Okay, so this moment equation, mx plus 32.78. Okay, 32.78, this is 32.78 multiplied by this dimension. This dimension equal to 0.6x, 0.6x plus 40 multiplied by this dimension. This dimension equal to 0.8x, 0.8x, and then you consider this UDL 10. This UDL 10, intensity 10 multiplied by, because now x we follow the length of this UDL, so 10 multiplied by x multiplied by half of the x. That's why you have a 10 x squared divided by 2. This is the third equation for primary structure. So you have this equation. Then we go for the redundant structure number 1. Redundant structure number 1, similar what we did for M0 here. Cutting number 1 and number 2, you have the same moment equation. Okay, because if you look at here, 1 and number 2 have same moment equation, similar to M2. Cutting number 1 and number 2. And again, you calculate moment equation cutting number 1 and number 2, and you consider clockwise moment as a positive value. So mx plus 4/9 multiplied by x. And cutting number 3, you consider left hand side structure, minus mx plus 4/9 multiplied by this distance. This distance equal to 0.6x, as mentioned here. Okay, as mentioned here. Okay, done for M1. Then we move to M2. Cutting number 1 and number 2, they have the same moment equation. For cutting number 2, they have 1 kilonewton meter moment here. So mx So you calculate moment at the cutting, mx plus 1 from the moment plus 1 from the moment minus moment due to this 1 over 9 force, 1 over 9 multiplied by x, so this is the moment. And then cutting number 3, to consider left hand side structure. Again we calculate moment at cutting number 3 here, minus mx minus 1 over 9 multiplied by this distance, horizontal distance. Horizontal distance means 0.6x as mentioned here, distance, because x you follow the incline. Okay, so settle for bending moment equation for structure number primary structure, redundant number 1 and redundant number 2. Then you tabulate in the table form. Then again you calculate all the deformation here. You substitute into our compatibility equation by using your calculator. Then you can determine your Cx and Mc by using that this calculator. You can determine Cx and Mc, because Cx and Mc is your redundant forces. After you have determined the redundant forces, now you apply in your actual structure. But now of course Cx and moment, they have a value here. So your unknown now, Cx, Ay, Ax, you have 3 unknown only. So you can use your static equation. You can use the 3 static equation. So you can determine Cx, Ay, Cy, Ay, Ax. Then I've verified using software Limpro, and you have a value, and this value justify with what we calculate by using manual calculation. Okay, thank you. Assalamualaikum.